Hey guys, welcome back to another video, and today we'll be discussing about an operating system algorithm, which is the process scheduling algorithm. So this is like one of my favorite algorithms, FCFS, because it's like one of the easiest ones there is. So FCFS stands for first come first serve, and you can like see the actual implementation of this algorithm in like ticketing counters where the first person to come would get the ticket. So your OS also follows this algorithm when it comes to like process scheduling. So in let's say like you have multiple processes that are in the ready state and you have only one CPU to work with. So how would your OS handle this situation? Because there are multiple processes that are wanting your CPU resources, but you need to like do this in a proper way so that everyone can work properly, right? So in this case, your OS uses FCFS, where the process that comes first gets the CPU. So in this case, P0 comes first, it gets the CPU. P1 then comes next, it gets the CPU then, and the process goes on. So one of the like biggest things that you have to keep in mind when it comes to FCFS is that the arrival time. So when the process that comes first gets the CPU first, and most important thing, that this is a non-preemptive type algorithm, meaning when P0 gets the CPU, it would get its work done. After that, another process can come in. So let's say P0 has started its work and it's going on, and suddenly P1 comes in. So your OS wouldn't switch between them. It would let P0 do its thing, it would let it work, then P1 can take the CPU and makes use of its resources. So this is why it's called a non-preemptive algorithm. So let's just look into an example to better understand how things work. So this is like an example that we are given with, and we have to like find out the turnaround time, waiting time, response time, and whatnot. So let's just get into it. So P0 is a process that comes first, as it's like in the 0 second. So 0 second is like a relative time. It's not like 10:30 a.m. and another process comes like at 10:31 a.m. It's like a relative process, relative time, and 0 second represents when the CPU started to work. So P0 comes at the moment the CPU started. So at the 0th second, P0 comes into play, and the burst time is 3 seconds. That's why, so it would work for 3 seconds. As I said, it's a non-preemptive process, so any process that comes in between the working of another process we cannot shift, we cannot switch between processes. So P1 comes at second number 2. However, P0 was working until 3 seconds, so there isn't any switch. So the next in line is P1, and P1 has a burst time of 5 seconds, so that would be 8 seconds. At 8 second, P1 would be done with his work, and in the 7th second, P2 comes into play. So P2 is next in line to get the CPU. So P2 works for 1 second, as its burst time is 1 second. So this would be 9 seconds. Then after that, in the 9th second, another process P3 comes into play. So P3, and it has a burst time of 7 seconds. So this would be 16 seconds. And on the 10th second, P4 comes into play, and it would work for 3 seconds. So P4 works for 3 seconds. So in 19 seconds, all the processes would be done for. Okay, so let's let's fill up this main table, which is like the main answer for this question. So our main task here is to fill up this table, and so let's just dive into it. So the processes are P0, P1, and we're going to maintain a sequence. So P0, P1, P2, P3, P4, and the sequence is basically when each process gets the CPU. So P0 gets it the first, and P4 gets it the last. The arrival time of P0, so let's just fill this table up. So 0 2 7 9, 10. And the response time of P0 is 0 because it got the CPU the moment it got into the RAM. P1 got the CPU at 3 seconds and it came at 2 seconds, so this would be 1. P2 came into play at 7 seconds and P2 got the CPU at 8, so the difference is 1. P3 got the CPU at the 9th second and the arrival time was 9, so it didn't have to wait anything, so 0. And P4 came at the 10th second but got the CPU at the 16th, so the response time was 6 seconds. Now the turnaround time is basically the completion time, when the process is completely done, minus the arrival time, when the process came into the RAM. So the process came into the RAM and it was completely ready to get the CPU, and so the turnaround time is when the process is done minus when it came into the RAM and was waiting for the CPU. So P0 is the completion time is 3 minus it came at 0 second and the turnaround time is 3. For P1, the completion time is 8. It came into play at 2, so the turnaround time is 6. For P2, the arrival time is 7 and the completion time is 9 and the arrival time is 7, so this is 2. For P3, the arrival time is 9 and the completion time is 16 and the arrival time is 9, so this would give us 7. And for P4, the completion time is 19 and the arrival time is 10, so this gives us 9. Now the waiting time is basically how long it had to wait to get the CPU. So for FCFS, we are not considering any IO interruption, so there's no in-between waiting times. So it's just like when the CPU came into the RAM and waited for, when the process came into the RAM and waited for the CPU. So the waiting time is basically the turnaround time minus the burst time. So for this case, for P0, so that's like 3 minus the burst time was also 3, so 0. So P0 didn't have to wait, and we can see this from the diagram here. So P0 started from the moment the CPU started to work. For turnaround time of P1 was 6 and the burst time was 5, so the waiting time was 1 second, and which we can see that like P1 came into the second, however it had to wait for 1 second for P0 to complete. For P2, so turnaround time is 2 and the burst time is 1, so I had to wait for 1 second. P3, turnaround is 7 and the burst time is also 7, so that is 0. And this is 0 because P3 came into the 9th second and the CPU opened up at the 9th second, so it was ready to get another process, so it's just like matched and P3 didn't have to wait a second. And for P4, like the turnaround time is 9 and the burst time for P4 is 3, so it had to wait for 6 seconds. And if you look into this carefully, you can see that the response times and the waiting times are the same, and this is the case only for FCFS, where the response time and the waiting time would always be same. So if you are like in your exams and you want to check your answers, you can do it in this manner. So response time and waiting time would always be the same value. So let's just look into another example to show you the convoy effect. This is like one of the problems of FCFS, and so let's say we are given these 3 processes and all of their arrival times are at 0 second and their bursts are different. So P0 comes first, and as like 3 processes with the same arrival time, we would consider them alphabetically. So P0 would come first, and it would start at the 0th second, so P0, and would work for 24 seconds because this is a non-preemptive type algorithm. Then we can have P1, which would work for 3 seconds, so that would be 27 second. And then we have P2, which would also work for 3 seconds, so this would give us 30 seconds. So if we write their process down, and we can see the waiting time for P0 is 0 and the turnaround time is 24 seconds. For P1, the waiting was 24 seconds, which is a lot, and the turnaround time was 27 seconds. And for P2, the waiting was 27 seconds and the turnaround was 30 seconds. Now if we look into this chart right here, or this table right here, we can see that the waiting times are a lot, and the average waiting time for all the processes would be 0 plus 24 plus 27 divided by 3, which would give us 17 seconds, which is a lot. That means that each process has to wait 17 seconds after it comes into the RAM and is waiting for the CPU. So 17 seconds is a lot. However, if we had the opportunity to make sure that P1 or P2 gets the CPU first, then we would definitely have much lower waiting time. So if P1 works first, it would have a 0 waiting time. Then P2 would have a 3 waiting time, so 0 plus 3, and P0 would have waiting time of 6, so that would be 9 divided by 3, so 3 seconds of waiting time for all the processes, which is like much less than what we had in 17. So this is like one of the problems. So this is called the Convoy effect, and to solve this we have SJF, which stands for shortest job first, and we'll be looking into this algorithm in a later video, but this is all about FCFS, and I hope you guys did like the video and understood something from it. And if you have any comments or suggestions, feel free to comment down below. Thank you.